Bell ringer. Find the areas of the triangles with the given information. Remember to use law, sine, cosine as needed, and use the function f of x equals x minus 1 over x to find f of 2 and f of 3. Go ahead and pause the recording and complete this, and then you can put your answers on the Nearpod Draw It slide that is entitled Bell Ringer. Example 3. What is the sequence pattern? 1, 1/3, 1/9, 1/27, so on and so forth. Well, what I notice here is that these denominators are all powers of 3. So if I just started with the 1/3, I could write that as 1 over 3 to the first power. 1/9 is 1 over 3 to the second power. 1/27 is 1 over 3 to the third power. So if we look at this pattern, it makes sense that 1 is 1 over 3 to the 0 power. And 3 to the 0 power equals 1. So our sequence, we can write a sub n is equal to 1 over 3 to the nth power. Example form. What is the sequence pattern? Well, we see we have 1, 3, 5, and 7. Go ahead and pause the recording and determine what the sequence pattern is. Well, we notice that the difference between the 1 and the 3 is 2, between 3 and 5 is 2, and between 5 and 7 is 2. So basically, it's almost like we're multiplying a previous number but by 2, but we have to do something else to it. So 1 is equal to 2 times 1 minus 1. 3 is equal to 2 times 2 minus 1. 5 is equal to 2 times 3 minus 1. 7 is equal to 2 times 4 minus 1. So our sequence pattern, B of n, is 2 times n minus 1. Factorial. This might be a new term to you. It says if n is greater than or equal to 0 is an integer, the factorial symbol, n factorial, that's that exclamation mark, means factorial, is defined by as follows. 0 factorial equals 1. 1 factorial equals 1. N factorial is equal to n times n minus 1 times n minus 2, n minus 3, n minus 4 times 3 times 2 times 1 if n is greater than or equal to 2. So if n is equal to 0, then it's always equal to 0 factorial is always equal to 1. 1 factorial is also always equal to 1. But if I had 5 factorial, okay, my 5 is the n, so my first term here is going to be 5. Then I'm going to subtract 1, and that's going to be times 4. Then I'll subtract 1 times 3, and I go all the way down until I get to 1. Then I would multiply those together. 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120 times 1, so this is equal to 120. Recursive sequence. A recursive sequence is a sequence where the first term or the first few terms are given along with a formula that specifies the nth term. For example, let's suppose that I say that S1 equals 1, and the sequence or the term S sub n is equal to n times S sub n minus 1. So S sub 1 equals 1. So S sub 2 is going to equal 2 times S sub 2 minus 1. Remember that in this case, n is going to be this factor, and I am going to subtract 1 to get to the previous term. So S sub 2 is 2 times S sub 2 minus 1. Well, 2 minus 1 is 1, so S sub 2 is equal to 2 times S1. That's 2 times 1, which is equal to 2. S sub 3 would be 3 times S sub 3 minus 1. So that's 3 times S sub 2, which is 3 times 2, gives me 6. S sub 4 would equal 4 times S sub 4 minus 1. So that's 4 times S sub 3. 4 times 6 is 24. S sub 5 would be 5 times S sub 5 minus 1, which is equal to 5 times S sub 4, which is 5 times 24, equals 120. That's an example of a recursive sequence. A Fibonacci sequence is shown below. It says write the first 5 terms of the given recursive sequence. Well, we have u sub 1 equals 1, u sub 2 equals 1, u sub n equals u sub n minus 2 plus u sub n minus 1. All right, so I know u sub 1 equals 1, u sub 2 equals 1, it's given. U sub 3 is going to equal u sub 1 plus u sub 2. Okay, 3 minus 2 is 1, and 3 minus 1 is 2. So that's going to be 1 plus 1 gives me 2. U sub 4 is going to be u sub 2 plus u sub 3. So that's 1 plus 2 gives me 3. U sub 5 is going to be u sub 3 plus u sub 4. So each time we're taking the 2 previous terms and we're adding them together. 2 plus 3 equals 5. Okay? So again, the terms of a Fibonacci sequence are the sum of the 2 previous terms after the first 2. Summation notation. If I have an expression where I'm adding several terms of a sequence, I can use summation notation to indicate that expression without having to write out each term as you see below. For example, I have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and that would be on and on and on until I get to the last term, which is plus a sub n. Well, I can use this symbol sigma, that is the Greek letter sigma, and I would say that this expression is equal to the summation as k goes from 1 to n of a sub k. Now, this particular k in this case is called the index. Okay, so the index is going to tell you the first subscript right, that we will be using in this summation. Here we list some properties of sequences using summation notation. These properties are useful for adding the terms of a sequence algebraically. Here are some formulas for sums and sequences. So if we have a sum, the summation of k equals 1 to n of c, then that means we're just going to be adding c over and over again until we get to n. So this is equal to Cn. Here's one that's similar to the example we just did. The summation of k equals 1 to n. K is changing. Here we have C above it. C is a real number. It stays the same. So that's why it's different. And when you are doing this type of summation, it is actually equal to n times the quantity n plus 1 divided by 2. When we do it, the summation as k equals 1 to n of k squared, that means we have 1 squared plus 2 squared plus 3 squared all the way up to n squared. That is going to equal to n times n plus 1 times the quantity 2n plus 1, all divided by 6. And similarly, you see the formula for the summation of k to the third power. So these are useful formulas. Example 5. Write out each sum. Here we have the sum as k equals 1 to 10 of 1 over k. So what we're going to do, we're going to let k equal 1, so that would be 1 over 1. Since we have the summation, that means we're going to add to it the next term, which is 1 over 2 plus 1 over 3. We will continue in the same fashion. So I put the plus sign, then set of ellipses, plus, and then 1 over 10. The only thing that I would change now is go back and rewrite 1 over 1 as 1. For the next one, we have the summation as k goes from 1 to n, k factorial. So that is going to equal, we'll start with 1 factorial plus 2 factorial plus 3 factorial, and then we could plus and then on and on and on, plus n factorial. Example 6. Express the sum using summation notation. Use 1 as the lower limit of summation and I for the index of summation. Here we have 1/3 plus 1/2 plus 3/5 plus on and on and on until we get to plus 6/7. So here we need to find the pattern. Well, when you analyze the different terms, you might notice that if you change the 1/2 to 2/4, now we see 1, 2, 3 in the numerator, and we see 3, 4, 5 in the denominator. So if we rewrote 6/7 as 12/14, then we can see how the pattern is changing. So we have 1 over 1 plus 2, 2 over 2 plus 2, 3 over 3 plus 2, so on and so forth. So we can see that this numerator and the first term of the denominator is the same, and that we are adding 2 each time. So how would we write that? That's going to be the summation. We're starting with I equals 1, and we go to 12. I over I plus 2. Example 8. Express a sum using summation notation. Use 1 as the lower limit of summation and I for the index of summation. So we have 3, 6, 9, on and on and on. 3 plus 6 plus 9 plus on and on to 18. So I notice these are multiples of 3. 3 times 1, 3 times 2. So I am adding up 3 times the index, starting with 1, 2, 3, all the way up to 6. So summation would be, as I equals 1 to 6, we have the summation of 3 times I. Example 9. Express the sum using summation notation. Use a lower limit, not necessarily 1, of summation and k for the index of summation. So we have 7 plus 8 plus 9 plus all the way up to plus 27. So I noticed I'm starting with 7. I'm just using consecutive numbers. All right, so basically I'm going to start with 7. So k equals 7, and then all the way up to 27. It's just the number that I'm adding, nothing else. So that's it.